Hello everyone. In this video, I'll cover the basics of tensor analysis. Let's begin with two reference frames, S and S prime. The spacetime coordinates in S frame can be denoted by x mu. This is equal to ct, x, y, z. Note that this mu over here runs from 0 to 3 and x mu is just a shorthand of writing these spacetime components. So ct is x0, x is x1, y is x2 and z is x3. Now when we go from S reference frame to S prime reference frame, we have new set of coordinates associated with S prime frame. These will now denote by x prime of mu. This is equal to ct prime, x prime, y prime, z prime. Now I'll define what is a tensor. For that, let's take a quantity A. This has, let's say, components A mu in S frame and A prime of mu in S prime frame. Now for A to be a tensor, there should be a particular relation among this A mu and A prime of mu, which I am writing down now. So A prime of mu is equal to del x prime mu upon del x nu A nu. Here I am using Einstein's summation notation, so nu is termed over. So if this relation is valid, then and only then A mu is a tensor. Or to be more specific, A mu is a rank 1 contravariant tensor. Contravariant. I'll come back to another type of tensors called covariant tensors, but let's absorb this definition for now. On one side you have components in S prime frame and on the other they are related to the components of A in S frame. This A nu is related to A prime of mu in this particular way for A to be a tensor. Now let's take an example of this. So we have dx prime mu over here, and by chain rule of calculus, this can be written as del x prime mu upon del x nu dx nu. This is just from the chain rule used in calculus. You can refer it in some calculus text if you don't remember it. So we have this relation. Now comparing this with the above relation, we can see that dx prime mu is in fact transforming like a tensor. So it is a tensor. We conclude that dx prime is a tensor. Sorry, dx mu is a tensor. This rank 1 contravariant tensor is also called a 4 vector. Now I'll define what is a covariant tensor. So let's say we have a quantity B mu in S frame going to B prime of mu when we go to S prime frame. So let me write that down. S goes to S prime. For this to be a covariant tensor, this should transform as B mu prime is equal to del x nu upon del x prime mu B nu. This is the definition of covariant tensor. B mu is a rank 1 covariant tensor. Now you can see the factor over here in this definition and the factor in the contravariant tensor definition. It's just reverse. To be more clear about this, I'll again once more write these definitions side by side. First, let's write the contravariant tensor definition. A prime of mu equal to del x prime mu upon del x nu A nu. This is a contravariant tensor. and we'll write the definition of covariant tensor using the lower index. A prime of mu is equal to del x nu upon del x prime mu a nu. This is our covariant tensor. So you can see the factors over here, this factor and this factor, it is just flipped for covariant tensor. Now let's take a scalar field phi, which is like invariant in all reference frames, and see how its derivative with respect to x mu transforms. So this goes to del phi by del x prime mu, because phi is remaining the same in both frames, it's a scalar by def. So again, by chain rule, we can write del phi by del x prime mu as del phi by del x nu into del x nu upon del x prime mu. Now for clarity, I'll write the second factor first, del x. You'll see it is same as the definition of our covariant tensor. Now see this expression in the brackets over here and see this covariant tensor definition. We can see that this quantity over here, del phi by del x prime mu, does indeed transform like a covariant tensor. So it is a rank 1 covariant tensor. So far we have been seeing rank 1 tensors, that is, we have just one index. Now let's go to rank 2 tensor. Now here you have two indexes over here, and these should transform contravariantly. So if t mu nu is a tensor, then it goes to t prime mu nu, and this is when, I'll write this again under transformation of coordinates. T prime mu nu should be equal to del x prime mu upon, let's say, del x alpha, del x prime nu upon del x beta, t alpha beta. See, it is transforming like contravariant tensor with respect to mu and nu over here. You can compare this definition with the rank 1 contravariant tensor and you'll see the similarity. Now we'll take the rank 2 covariant tensor. This should transform covariantly with respect to mu and nu. So I'll write that down in a similar fashion. This is a rank 2 covariant tensor. Check these transformation factors over here, del x alpha, del x beta, and this upper part. And for rank 2 covariant tensor, it is transforming covariantly with respect to mu and nu. Now let's take a mixed tensor. We have one lower mu and upper mu and lower nu, t mu nu. Now this should transform covariantly with respect to nu and contravariantly with respect to this upper index mu. So how will this transformation look like? So t mu goes to t prime mu nu, and this should go contravariantly with mu, so I'll write this first, and covariantly with nu, the lower index. So that factor will be del x beta by del x prime nu t alpha beta. T alpha beta. This is called a mixed tensor. It is again rank 2 contravariantly transforming with respect to mu and covariantly with nu. Now, just for the sake of example, let's take a rank 4 tensor, 2 lower indexes and 2 upper indexes. So it should transform covariantly with respect to AB and contravariantly with CD. This T ABCD, let me clean this up, goes to T prime ABCD under the change of reference frames. This should be now equal to, let's transform the CD first, contravariant factors, del x prime C upon, let's use P, del x P, into del x prime D upon del x Q. See, the primes are coming in the numerator for contravariant transformation in. And then we have del x R by del x prime A into del x S del x prime B. I'm actually running out of space here to write this T properly, so I think I should yeah, this is T of PQ in upper index and RS. Actually, I'll just write this whole thing down once more. Let me clear up some space. T prime CD AB del x prime C upon del x P, contravariantly with respect to CD over here, into del x R upon del x prime A. Yeah, let's clear all this, it's not looking nice. Del x S upon del x prime P. See the covariant transformation with respect to A and B. And here we have PQ, contravariant, and RS. So this is how the tensor, this mixed tensor should transform. Thank you very much.